All right, everyone, welcome. This is your focused review for the Thermodynamics quiz on April 15th, 2026. We're going to cut right to the chase and zero in on exactly what you need to know from Chapter 5 to completely nail this thing. Okay, so here's our game plan. First, we'll talk about the core problem you'll face on the quiz. Then we'll introduce the master key to solve it, show you the bridge that connects it to everything else, and we'll wrap up with a really powerful shortcut and some final tips. Let's do it. So, your quiz is almost certainly going to ask you to do one main thing. Calculate big macroscopic properties like pressure or entropy using the tiny microscopic details of a system. The entire point of this chapter is building that connection. And that's the big question, right? How do we actually build a bridge from that quantum world of individual energy levels, the stuff we can't see, to the classical world of thermodynamics that we can actually measure in a lab? Well, the answer, and pretty much the first thing you should always calculate in any of these problems, is something called the partition function. We call it z. Honestly, you should think of z as the main character in the whole story of Chapter 5. So what is z, really? Well, it's just a single number that basically packs in all the statistical info about your system at a certain temperature. It's a sum over all the possible energy states, and each state is weighted by this thing called the Boltzmann factor. That factor just makes high-energy states less probable, which, makes sense. So Z is really just a super compact way of describing how all the energy is likely to be shared or partitioned. And here we've got a perfect example, straight from your lecture notes, for a single particle in a one-dimensional box. On the left, you see the formula for Z is this big sum over all the energy states. For each state, we're adding up the Boltzmann factor. Now, the key takeaway here, and you'll see this in problems, is that when the temperature gets high, in the classical limit, we can ditch that complicated sum and approximate it with a much, much simpler integral, like you see on the right. Okay, so once you've done the work and you have Z, you can unlock literally everything else. And you do that through something called the Helmholtz free energy, which we call F. If Z is the key, F is the door it opens. Now listen up, because this next formula is the absolute heart of this entire chapter. If you only have enough brain space to memorize one thing for this quiz, make it this. F equals minus kBT times the natural log of Z. So simple, right? But this little equation is the bridge. It connects the partition function, Z, which has all that microscopic quantum state information, to the Helmholtz free energy, F, which is this incredibly powerful macroscopic property that lets you find everything else. And you can see how important it is right here in your own notes. I mean, the text says it right there. Once F is known, it's straightforward to get other thermodynamical properties. That's the whole point. All that hard work you did to find Z pays off right here, because now you have F. So let's actually see how this works. This whole process is a repeatable strategy for solving problems. Mastering this next part is where you're going to score most of your points. For example, let's say you need to find the pressure. It's easy. You just take the partial derivative of F with respect to volume while keeping the temperature constant. It comes straight from that fundamental relation for dF. And your notes lay out the exact derivation right here. Look at the bottom. You can see the formula for pressure. P is just the negative partial derivative of F with respect to volume. And since F is really just a function of Z, what you're actually doing is taking the derivative of the natural log of Z. You just plug in your expression, turn the calculus crank, and out pops the pressure. And it's the same story for entropy. To find it, you just take the partial derivative of F again, but this time with respect to temperature at a constant volume. The logic is exactly the same. All the information you need is already packed inside F. And from there, everything else just falls into place. The internal energy, U, is just F plus T times S. And once you have U, the heat capacity at constant volume, CV, is just its derivative with respect to temperature. See? It's a chain reaction. Here's a full example from the notes showing the calculation for heat capacity, CV. Notice the pattern here. It's all about derivatives. You see the formula for S is a derivative of F, and then CV is related to the derivative of S. It's like a cascade of calculations. And the one thing you have to remember is that it all starts with calculating Z. Okay, so this right here, this is your ultimate quiz cheat sheet. Seriously, memorize this table, calculate Z, find F, and then just use these relationships. It's your roadmap. Now, for some problems, especially ones with classical gases at high temperatures, there's a really powerful shortcut you can use. If the conditions are right, this thing can save you from doing a ton of calculus. It's called the equipartition theorem. It sounds a little fancy, but the idea is actually super simple. It just says that for every term in the energy equation that's squared, things like velocity squared in kinetic energy or position squared for a spring, the system gets, on average, a little packet of energy equal to 1/2 kBt. So, to use this shortcut, you literally just count the squared terms. For a normal diatomic molecule, you've got 3 squared terms for moving in x, y, and z. You've got 2 for rotation, so that's 5 total. The average internal energy, U, is just 5 times 1/2 kBt. Done! Then, to get the heat capacity, CV, you just take the derivative of U with respect to T. So much faster. Okay, let's wrap this up. I want to hit one more key concept and give you some final tips so you are totally ready for this. Understanding the why behind this stuff really helps you remember the how. And finally, let's make sure you understand the fundamental difference between heat and work. This is a huge conceptual point. Look at the diagrams from your notes. When you add heat to a system, the energy levels, E1, E2, E3, they stay put. The particles just shuffle around, with more of them jumping up to higher levels. But when you do work on the system, like compressing a gas, you are physically changing the system, which actually shifts the energy levels themselves. It's a critical distinction. So on quiz day, this is your strategy. Step 1, always start with Z. Just do it. Step 2, find F using that magic formula. Step 3, know which derivatives to take to get S, P, and U. And before you start all that math, just ask yourself, hey, can I use the equipartition theorem here? It can be a massive time saver. And please, please watch your units. Mixing up KB and R is such a classic mistake. Good luck on your quiz on April 15th. You have all the tools you need. Now, just go use them. You've got this.